yourself for digital part, and some of them are analog people and they contribute for analog part. Once if we integrate analog and digital combined together and then we try to make a chip, once a chip is ready, then we try to send it for fabrication. So before fabrication, what we try to do is we try to verify our design. Okay, so in most of our design perspective, what we first do is verify our design. In your digital system design courses, you might have seen that sort of verification of your design. You might have done multiplexers and counters and register. Initially, you try to design it and then you try to verify your design by applying sort of stimuli, and you try to verify that your design work, your design which is going to work for which is going to work as per the intended stimuli or not. Okay, so what we have to understand from here is that we first design our verification and then we go for test our design. There is a difference between designing and testing, or you can call it as verification as well as a testing. Okay, so the need of testing is that to determine the presence of fault in a given circuit. The purpose of testing is that to determine the presence of fault. And we also discussed while talking about the layout and other perspective, we had seen that we are trying to follow the minimum guidelines given by the foundry, that is minimum width of your wire and minimum length of the wire, right? So which gives us that how to avoid the some of the what you call faults or malfunctions that are going to be present inside of our design, and that can be noticed while verifying our design. Okay, so the purpose of testing is to determine the presence of fault in a given circuit. Okay, so before testing it, what we normally do is verification, right? We try to verify our design. So verification is nothing but before designing your, before testing our design, we try to verify that our design is correct or not. Okay, so verification is also referred to be one kind of testing which verify the correctness of our design. Okay, you can call it as sort of testing is a verification. One kind of testing is referred to be a verification process, and which verify the correctness of our design. But what we need to remember here is that the chip is not get fabricated yet. Okay, so before fabrication, we try to verify it. That is called as verification. So what we have to remember here is that there is a difference between design verification as well as a testing, right? So after design, we try to fabricate it, and before fabrication, we try to verify our design. So let's talk about some of the things which are related to verification and testing. So let me write here some of the terms which are related to verification and testing. So if I write verification and testing, what is the verification and what is testing? If we noted down some of the points related to verification and testing, are trying to understand what exactly the difference between testing and verification, right? Verification tells us that it verifies correctness of our design. Whatever the design we are trying, whether it is correct or not, that is going to be verified through the verification process. Whereas in case of testing, verifies correctness of manufactured hardware. So this is the difference. So verification is that first we try to design it and then we verify that our design is correct or not. So we will verify that correctness of our design. Whereas testing, verify the correctness of manufactured hardware. Means after design only we'll go for fabrication. So after fabrication, we try to verify that the fabricated chip is going to work or not, right? And the second difference is, this is verification is performed by simulation or formal methods. Hardware stimuli also we apply, and we try to verify that our design is correct or not. Okay, so and we will try to use sort of tools. We use some of the EDA tools, and then we try to verify our design. Whereas in case of testing, what we try to do is this testing is two process or two. It consists of two parts. One is test generation, and second one is test application. So it is two-part process. The first part is test generation, and second one is test application, right? So here we have hardware, and then we try to use the hardware, and for that hardware we try to generate a first try to generate our test generation vector, and we apply the test generation vector, and we verify that our hardware is going to work as per our design specification or not. Third one is this verification is performed once prior to manufacturing. So before manufacturing, we try to verify it, and we call it as verification process. And whereas this one is test application performed on every manufactured device. Okay, what we do here is test application or test vectors performed. Test vectors are applied on every manufactured device or hardware. Okay, on every device we try to apply a test vector and we try to verify it. And the last one is here this verification is responsible for quality of design. Right? How good our design is. That will define you that how qualitatively we are designing our chip. Whereas in case of testing, which is responsible for quality of devices, right? So once you test it, then it will define you the how qualitatively your hardware is going to be work. Okay, so these are the some of the major differences between verification and testing. So verification tells us that how correctly we are designing our chip, and testing will tells us that how correctly we are manufacturing our hardware, or what is the correctness of the manufactured hardware, whether it is going to be correctly functioning as per our application or not. And the second difference is the verification is performed using sort of simulations, whereas testing is performed with two parts. One is test generation, other one is your test application. So test vectors we need to generate, and test vector we need to apply for the hardware, and we verify that this hardware is going to be work as per our desired or intended application or not. The third difference is that this verification is performed prior to the manufacturing, and this testing is performed on every manufactured device. This verification is responsible for the quality of the design, whereas testing is responsible for quality of the device, how the device is going to be work, how correctly the device is going to be work. And here, if there is any malfunction in your verification and testing, if there is a fault in verification, then what you can do is you can go for redesign it, because chip is not yet fabricated. So verification is done before fabrication and testing is done after fabrication, right? So if there is any fault in your design, because you are trying to design it, and then you can send it for redesigning your chip. Whereas in case of testing, it is designed first and then it will go for fabrication. After fabrication, you are checking that if your chip is or your IC is not going to work fine, then what you need to do is you can just throw it out. You cannot use that IC for your intended application, right? Let's say it is a processor and you try to fabricate a processor and that processor is not working fine as per your requirement, then you cannot use that processor for your system application. But if there is any fault in design, but you can redesign it back because chip is not yet fabricated, right? So verification is before fabrication and testing is after fabrication. This is what you can remember in a crude way, that the difference between verification and then testing, right? Now, in CMOS ICs, there are majorly three IC testing methods are there, or you can call it as CMOS IC test. CMOS IC test are classified majorly in three categories. First one is referred to be functional or functionality test. You can also call it as logic verification. What do you mean by logic verification or functionality test? It verifies only the functionality of the chip using simulation tools. You can use sort of simulation tools and you try to verify that what is the functionality of the chip. That's it. Okay. Could not go in detail of that, but whether this design logic is verified using sort of simulations, right? And the second one is your silicon debug, right? What is silicon debug? It is used to find the debugs on a chip. Means if there is any fault on a chip, and it is an expensive process because it is conducted on every chip before it is going to be shipped to the customers. Okay, every chip need to be tested, and which is expensive than the functionality test or logic verification, because every chip need to be verified. Okay, the third one is your manufacturing test, or you can call it as gate level testing, right? What do you mean by manufacturing test? Test is conducted on each and every chip before shipping to the no, sorry, let me recorrect the silicon debug here. Silicon debug is that it is used to find the debug on the chip because it is tested by feeding it onto the system. So you need to just connect your chip to the system and then you try to verify your design, right? So that is what your silicon debug. Whereas coming to your manufacturing test, this test is conducted on each and every chip before shipping it to the market, whether the silicon is intact with with the interconnect wires or not. Okay, so while talking about our layout part and then what do you call stick diagram, we talked about the connection between the metal layers, and if there is any misconnection between one wire to another wire, what are the consequences that we had seen. If that is going to happen while manufacturing, then the chip is going to be the chip leads to malfunctioning of your functionality. So if there is a short circuit between one metal layer to another metal layer, then chip will not work as per the intended application. It means chip is going to be referred to be a faulty because of a small mistake. Or while talking about the fabrication of our chip, we had talked about the clean room process. If you are not following the clean room while fabricating your chip, there are some dust particles, and these dust particles causes a lot of damage to your chip, and that can be detected while testing your chip, right? You cannot directly detect whether this dust particles are there on your metal layers, or which is going to shortening the to conducting layer or not, or whether it is there on your gate and source layer, and these two gate and source layer are shortening or not. That can be detected once the chip is going to be tested, right? So testing is an important criteria, and this can be classified into three main categories. First one is a functionality test, second one is silicon debug, and third one is manufacturing test. And this testing can be done, let's say we have a IC, and this testing can be done at various levels. Okay, this testing can be done at various levels. So let me write it down that testing is done at several stages or levels. Okay, so you can notice that there are varieties of testing. So if you remember correctly, while talking about our processing step, before start our fabrication, fabrication of our chip, then first what we try to do is we try to test our wafer, right? So we first try to test our wafer, and wafer is defective free or not. If it is defective, then we're not going to take the wafer itself to start our manufacturing process, right? So first we have to test our wafer, and that wafer is defective free, and then we'll start our fabrication. That's a different story before starting our fabrication. Now we started fabricating it, right? We started fabricating it, and we have a wafer. This is a kind of cylindrical disc, and which contains several dies in it, right? There are various dies in it. Let's say this is how we have different dies in our chip, different dies on our wafer. So you can consider that this is our die, where we have fabricated our chip. So this is our die. Okay. Now we haven't taken the die out of our wafer. It is there inside of the wafer. It is there in the wafer itself. Now what we do is we try to slice this vertically and horizontally, and we'll take the die out of our wafer. So before taking a die out of the wafer, we try to test it on the wafer itself. So we call it as testing is done at wafer level. So the first methodology or first level of testing is done at wafer level. Okay, so this wafer testing is different thing, and wafer level testing is different thing. So this testing of wafer is before start the manufacturing process, or before start our actual chip to be fabricated, or before start our actual processing step. But wafer level testing is after fabricating our chip, whatever we are trying to fabricate on a wafer, and once the process is done, then we'll not take the die out of the wafer, we'll test the die when it is on our wafer itself. So now we'll test this die which is on our wafer itself. So we call it as wafer level testing. Okay. And the second level of testing is that die is separated. Now we try to isolate our die, this one, and we pack it, right? So while packing it, then we try to test our wafer. So before isolating our die from wafer, we test it. That is referred to be a wafer level testing. Once it is isolated from the wafer, then we try to put it on the package. So before packing it, then what we do is we try to test it. So you can call it as package level testing. This is referred to be a second level of testing. And the third level of testing can be done at board level. Right? Once the die is there and then it is working fine, then we have kind of boards, that is this is placed on the package, and then now this IC which contains different pins, and of course you have different bonding pads and bonding wires are to be connected to all these pins. Now this IC is there and this IC is going to be placed on the boards. Now you have different PCBs and which contains so many number of chips, right? Some boards may contains 100 number of chips on it, right? Or you can call it as a PCBs. Now once dice are packaged on your given package setup, then it is going to be placed on the board, and now we'll try to verify that whether that board is working fine or not. If it is not working fine, once it is placed and packaged, then we send it back. At any stage, if you can identify that there is a faulty in the testing, then we'll not use it. We'll comment that this die cannot be used, and we can comment that this package die is not going to be used in the board. So if you are identifying that at board level your IC is not working fine, then you cannot use that IC in your PCBs, right? And the fourth level of testing is referred to be system level testing. Okay, now you have different PCBs. Your system may contains tens and 20 of PCBs in your system, and then you integrate all the PCBs together and you try to verify the functionality of your system, right? So now at this level, if you're identifying that if chip is not working fine, then you need to identify that which PCB is not working good, right? Now you identify the PCB. Out of that PCB, there are hundreds of your dies, and which hundreds of your packages, and which package is not working fine. And out of many packages, you identify that which die is not working fine. Okay. So once you integrate all the PCBs and then you try to verify or test it whether the system is working fine or not. And the last level of testing is referred to be the fifth level, which is referred to be field level testing. The last stage of testing is done at field level when an end user tests the system while using the system functionality. Now you have a system and which contain, let's say you are trying to purchase a system which contains your CPU and your TFT, as well as along with that there are some other equipmentary keyboard and then speakers. Now we integrate all the modules together and now you are trying to use it. Sometimes you may not give proper input to your system because your input device which is there and which is to be interfaced with your CPU is not working fine, and then you may not get the correct output from your system because your input device which is there is not giving correct input to the system, right? So at field level, you try to connect all the different modules which is required for your functionality, and then you try to test it whether your complete setup is going to be work as per your requirement or not. So these are defined to be different level of testing.
Seems like sir has. Okay. Seems like sir has a per card. Wait for a few minutes.
Please wait.
వెదర్ బాగుంది, మన కరెంట్ కూడా పోతున్నారు, జాగ్రత్త.
I guess now I am audible for both the section and video is, you can see my screen, right?
Yes, sir.
Okay. Both the sections, section A and B. Hemant?
Yes, sir.
Okay. Yes, we were talking about different level of testing, wafer level testing, wafer level testing. Before wafer level testing, we try to first verify the wafer, whether wafer is defective free or not. Once wafer is defective free, then we'll start with wafer level testing, and it can be done after fabricating our chip. Chip is not separated from the wafer, and we try to test it. If it is working fine, then we try to isolate the die from the wafer, and then we put it on the package, and then we try to verify that die is working fine or not. And now after that, if it is working satisfactory, then we put it on the board and we try to verify it again, because you cannot guarantee that I see if die is working fine at the wafer level, it may not work at the board level also, because there is a problem in packages also. There is a problem in slicing your dies from wafer also. So there are a lot of issues may take place while moving from one stage to another stage. So at every stage, we try to verify that manufactured die, and then we slowly move on from single die to complete field, complete system, which is there on the field. Okay. And once board level testing is done, then you integrate different boards and try to make your system, and if system works fine, and then now you can test it at the field level. Now the end user started using it, and user is going to be use different modules together along with your chip. Your IC is working fine, but sometimes it may not accepting the input and may not generating the correct output that trying to show on the screen. So there may be some interfacing issues while designing, while manufacturing your ICs, or while designing this ICs also. So these are referred to be some of the different levels of testing that one should go for testing. Okay. Now we call it as cost of testing. We'll try to see that cost rule. Okay. What is the cost that we try to see when we are trying to test the wafers? Okay. And we call it as rule 10, or rule of 10, that is normally referred to be testing rule. Let's talk about the first level testing, the top level. So this is referred to be your bottom level testing, and this is referred to be top level testing. Okay, assuming that we haven't tested our die which is there on the wafer, and we directly placed on the packaging system, and the packaging system package is placed on the board, and then boards are integrated. Different boards are integrated on the system, and then system is shipped to the end user. Now end user finding the difficulty that system is, the entire setup is not working fine. Now what the end user is supposed to do is, he try to see that out of input device and output device and CPU and other modules, which module is not working fine. Out of various modules that he is handling, which module is not working fine? That is the biggest task that one's supposed to start with, right? So you have an input device such as keyboard and mouse. If any one of these two components is not working, then you cannot give the data as you wish. Okay. Sometimes you are correctly applying the input, but the system is not properly projecting the output because of some problems in your output device. Now you need to accurately identify where the fault from the input device or output device or from your system itself. Assuming that you paid a lot of money and then identify that there is a problem in the system itself. Okay. And then you needed to see that what is the problem in the system, right? So that system contains different PCBs in it. At field level, you identify that there's a problem in the system. It means in the CPU. Okay. That CPU contains a lot of PCBs in it. So now you need to identify which PCB is not working fine. You have 10 to 15 PCB, let's say. Out of 15 PCBs, identify the one PCB which is faulty. You need to struggle a lot and try to identify that which PCB is not working fine. Now you struggle a lot and then identified one PCB is not working out of 15, and then take that faulty PCB and check that out of that PCB there are hundreds of packages or hundreds of chips that are placed on your PCBs. Now you need to identify which package is not working fine. Right? You need to test every package and see that which package is not working fine. You need to pay a lot of amount for that. And then you identify that with first package out of the 100 packages, you identify one package which is not working fine. Now you go back and then see that which after identifying the package and then see that whether there's a problem with the die or problem with the package, that you need to identify first. Now if you try to do that, then what you can see is that first you try to testing the wafer initial stage itself, then it costs, let's say, let me write it in the form of a dollars. It costs 0.01 to $0.1 per wafer level testing. Okay, and at every level we are trying to verify it. But you can see that you are trying to test your wafer. On the wafer itself, you identifying that the particular die is working or not. So this die is working properly or not, and it costs amount of $0.01 to $0.1 of rupees. Now you are testing this same die on the package, because you package different dies, and then you need to see that now if it is tested at the level of package level, then it costs from $0.1 to $1. Okay, because you have different packages and you need to identify which package is faulty. Now you are testing at system level or board level. Let's say this is your board level. At board level, it costs from $1 to $10. And now you are testing at, let's say, system level, then it costs to $10 to $100. Now you are verifying at the field level, then it costs hundreds of dollars to thousands of dollars. Okay. This is what we refer to be rule 10, because as you are moving from lower level to higher level of hierarchical system, from wafer to this final field, then the cost of testing is going to be increases 10 times from one level to another level. Okay, so as you are moving from wafer level to package level, then your die is going to be identified which die it is. Similarly, when you are testing at the system level, it is difficult to test which board is working, which board is not working fine, and then it costs a lot of money. Okay, so at every level we need to identify that which module is not working fine, and then we generally follow the bottom to top approach to identify the faulty in the chip. Otherwise, if you place it on the board and then you are going back and identifying it, if there is a fault in your wafer, then it costs almost $100 to $1,000 to identify it. But when you try to identify that itself in wafer level, then it costs $0.01 to $0.1 only. Right? So we call it as a rule 10 for testing of the wafer, testing of the system at every level, and this is how there's a variation in the testing cost at different level of design. At different level of testing, not design, it is different level of testing. Okay. Now, assume that after going through different levels and
Is not visible. The screen is not visible.
now is that okay?
Yes, sir.
I think for section A or section B, you guys have section A.
Yes, sir. Yes, section A.
People got disconnected. I think both the sections. Hello.
So seems like okay, so I'll burn now. ముచ్చట వేసేటప్పుడు ఒకసారి క్లాస్ టెన్ పట్టించుకోవచ్చు కదా మీ ఇద్దరు క్లాస్
Section A. Am I audible?
Now it's okay, sir.
Okay. Let me check with section B. Section B. Am I audible? Am I audible?
Sir, it's showing like you're joining from twice in the same link.
Yes, Hemant. Now,
So, now you're audible, sir, but there is no screen.
Kartika, is that okay now?
Sir, the screen isn't visible, sir.
Screen is visible.
Screen isn't visible, sir.
Screen isn't visible. Go and share the screen. One second. Now,
No, sir.
but here now is you can see the screen.
No, sir.
Now,
Now it's visible, sir.
okay. So now if you skip the testing at the initial stage, the presentation is not visible. Section A or section B? Section A or section B? Let me know it. Section B. Now, yes, sir, it's visible. Okay. So when you try to test it at the bottom level, then cost of the testing is very less. But when you are moving from bottom level to higher level, then cost of testing is going to be increases drastically. So what we have to do is we try to test at every level so that the cost of testing can be minimized. Okay. Now let's say that we have identified that there is a fault in the system. Fault nothing but malfunctioning. It means you are expecting output to be logic 1, but instead of that you are getting output is equal to logic 0. Or sometimes it may not be logic 0 or logic 1. Sometimes it is also referred to the high impedance state also. So instead of getting correct output, there is a incorrect output at the output of your entire system or circuitry. Okay, that is referred to be a fault in your system. Okay, so fault is defined as malfunctioning, which is treated to be a physical defects of one or more component, or you can consider it as one or more connections between the components in a given circuitry. Okay, how do you define fault? Fault is defined as it is referred to be a malfunction, and it is because of the physical defects of one or two components, or even called as one or more components, or even also call it as the connection between the components in a given circuitry. Okay, because of that there is a incorrect output at your circuit. We are defining the fault at the circuit level. Okay, what do you mean by fault model? Fault model is nothing but how fault occur in the circuitry and what is the impact of this fault on the circuit is defined as a fault model. Okay. Fault is defined as malfunction. Okay, it basically defined as malfunction. It is a physical defect of one or more components. Otherwise, a connection between the component and which causes to be faulty output or malfunction in the output. A fault model which defines you that how the faults are occurring and what is the impact of that fault on the circuitry, which is referred to be a fault model. Okay. Basically, there are two fault models that are present in our VLSI circuits. Broadly, we call them as the first fault model is stuck at faults, and second one is stuck open or stuck short faults. These are the broad classification of the fault. One is stuck at fault, second one is stuck open and stuck short faults. Let's talk about the first one, which is stuck at faults. Stuck at faults is nothing but there is a fixed value on your output line or a circuitry irrespective of your input that is going to be changed, and that fixed value could be either logic 0 or logic 1. Okay, what is stuck at fault? Stuck at fault, there is a line, okay, and that line is assigned to a fixed value 1. Because of that, the circuit is going to generate fixed output, and that output could be logic 0 and logic 1. Okay, a line which is connected to your circuitry that is going to be fixed at a value either logic 0 or logic 1. Because of the fixed value that is going to be connected, the output of your circuitry, this is the output of your circuitry, that is going to be also fixed to either logic 1 or logic 0. And that is referred to be your stuck at faults. Okay, and these stuck at faults are classified two types. One is stuck at 0, basically call it as stuck at 0 faults. Other one is stuck at 1 fault. Okay, what do you mean by stuck at 0 fault? When the signal line always present at a logical 0 is referred to be stuck at 0 fault. Let's take stuck at 0 fault and take an example of an AND gate which has two inputs and one output. Output is referred to be F, inputs are referred to be A and B. Stuck at 0 fault is nothing but a line which is A or B. Let's take a B line which is always connected to ground, right? It means as you change the input of your B 0 or 1, it cannot be reflected to your logic gate. Screen is
not visible now.
Section A or section B?
Section B.
Now,
Yes, sir. Now it's visible.
so take an example of an AND gate which has two inputs A and B and one output which is F. Now, one of their input line which is stuck at a value called as 0. So here 0 is represented with the ground line. Now this line is shorted with the ground, right? And which always gives the input is equal to 0. Because of this input, and your output is always going to be stuck at 0. And this is referred to be a stuck at 0 faults. Okay, when the signal line always present a logic 0 is referred to be a stuck at 0 fault. Other one is stuck at 1. Now in this case you take an example of an OR gate, right? And one of the input I can take A and B. Now A is stuck at logic 1. Now because of this logic 1, if you change the input here, you'll get output F is always 1, and this is referred to be